Welcome to my series, Architecture of Machine Learning Systems. In this series, we will talk about how to turn machine learning models into production-ready software solutions. If you are a data scientist or machine learning engineer or manager of a data science team, these videos are designed to help you make the right decisions so that your model becomes part of the application landscape in your organization and starts adding value. In 3 episodes, we go through the essential steps to create a design of your system, considering what needs to be done and how it can be done with best practices. First, we talk about why data science needs a software architecture and the steps you need to master. Then we go through them all. We talk about requirements and constraints and how not to forget any of that when you are building your solution. Once you have requirements, you have technical decisions to make. We think about strategies on how to do that, where to get ideas, how to deal with missing information. Next, once a decision is made, it needs to be communicated and documented. We will talk about how to do that to each group of stakeholders. And our final topic will be the employee perspective. What technical and non-technical decisions, what skills are needed, what opportunities are there to acquire missing skills. I also have a list of recommended books and I will share the slides both in description of the videos. One slide about me. I have been in IT since 2000 and various roles: Java developer, consultant, cloud specialist, DevOps guy, trainer, and architect. After discovering AI, I switched and now work in data science. I live in Berlin, am married, and have 2 children. You can find me on LinkedIn, on Twitter, and on Medium. So, I have laid out a simple scenario how working as an architect begins. Let's say you are working in a bank on a machine learning model for customer scoring. Since you are a skilled data scientist and also the quality of your data is sufficient, you soon have a model with very good performance. Once you present your result, managers or product owners from other teams approach you and want to integrate your model. Let's say a CRM team wants to have your scores for more accurate targeting people with offers and product recommendations. A credit department needs your scores when deciding whether to approve or deny a loan application. And a fraud detection team wants to incorporate your scores into algorithm to detect frauds. You might be happy about this, but if you primarily worked with Jupyter notebooks, you might not be sure how to deliver calculated scores. And then people start telling you that what they want, which takes it even more nebulous. So can we have all the scores recalculated every day? Can you deliver scores to sellers who work outside of our network? Can we identify customers whose scores have improved significantly in the last 12 months? And so on. Let me share with you a few ways you can integrate your model. We will just look at the serving part. In the next few minutes, I'm going to mention a lot of technologies. There is no need to think of them as suggestions and memorize them. I just want to show you how diverse the ways to productionize your model can be. This series is less about specific technologies and more about approach and methodologies. I have also a couple of recipes how to bridge the gap if you lack some technical know-how in the very last part. So the very first way to integrate your model would be to package it as a service that provides a RESTful API So once a client application needs a score, it sends the customer's data to your API. The data is passed to, for your model to predict. Once a prediction is calculated, the service returns a prediction result. Okay. Second, you can have a nightly batch which recalculates scores for all customers and stores them in a database. You keep the service exposing API, but in this case, the service only needs to do a lookup for the customer ID. The third option, your scores are written to a database. You leave it to your clients to read them using a query language like SQL. In a completely different way, you can use Cloud Functions. The Cloud Function is basically a piece of code deployed to the cloud, and once you use a data store in the same cloud, you can configure that when you make a change in your store, such as adding a customer or changing the data of an existing customer, it will trigger the function with your code. Once started, the function selects the customer data, initializes the model, calculates the score, and adds the score to the customer data. The type of reading remains the same with the query language. Option number 4. Another modification. The use of messaging middleware. Messaging middleware is a piece of infrastructure used to exchange messages between applications. Usually it has topics so that one application can publish messages in the relevant topic and any other application can subscribe to relevant topic to receive and deal with the message. So we keep the part where a change in the client data causes a recalculation of the score. But once the score is calculated, it is published through the middleware so that client application can receive it and update the scores in their data stores. And the very last option would be to deploy a model in a Spark cluster so that any client that integrates a Spark client can ask the model for a score. I have listed 6 different options, and you can be sure there are more, and for each option, there may be a context in which it would be the best solution. We also need to come up with scenarios how to update the model with fresh data. And again, there can be many alternatives. And we have mainly discussed integration patterns, but hardly any technologies to implement them. So you have to make decisions about data storage, if using a relational data storage or key value store or document store, about exchange protocol and format, about runtime environment, about deployment tools for logging and monitoring, way of scaling your solution if you get more customers. Think about cloud provider and services, third-party services you can also use, and much, much more. So you have many decisions to take, and sometimes you don't know how to do this in a qualified way. The discipline to make all these decisions systematically is software architecture. First, we can take a look at the definition from IEEE Foundation. So software architecture is defined as a fundamental organization of a system and its components and the relationship between itself and the environment that guides its design and evolution. But maybe it will be clearer if we look at the main phases what a software architecture includes. There are 3 of them. First, you need to gather all the requirements and constraints you need to consider. Second, you need to decide on structures and communication patterns and which technologies and tools used for implementation. And you need to make some strategic decisions as you are interested in integrating all the models in a similar way. So the goal is to build a solid solution once and adapt it for each new model with a minimal effort. And third, once decisions made, you need to communicate with stakeholders of your product, the management, the developers, the business, the infrastructure team, your suppliers, your customers, and so on. You also need to convince many of them to contribute to your solutions. So in next videos, we will look at all these phases in more detail. But before we do this, one last point. I know several books and courses on machine learning system design. They primarily describe working technical solutions for building the pipeline from raw data to production. Some of these books are extremely well done and clearly recommended for study. From my experience in the industry, all I can say is that the overall success of your solution requires more than just the technology, and it is not the technology that sets the limits what you can achieve. For this reason, I have created this series with a holistic approach and try to give you insights into all the disciplines you need. On the other hand, do not think of this series as a fully comprehensive education for software architecture. We focus on select practices that enable data science folks to integrate their models into the enterprise application landscape by keeping the focus on data science challenges. So let's get started. We focus on the very first phase of architectural work, requirements engineering. This is a phase where the most expensive mistakes happen. All the decisions you make, the implementations of those decisions, the communication with other teams, the integration work, the quality assurance, everything results only from the requirements. So every forgotten, misunderstood, or poorly documented requirement can mean a huge rework of your entire solution. Every stakeholder you should have asked but did not can mean this as well. I was told a very funny story recently. A major oil company posed a problem to data scientists, monitor whether truck drivers were following safety rules and when transporting gasoline, especially they were not smoking in the cab. After some time, data scientists presented a solution, a hardware module which looked perfect. It took videos, evaluated them with neural networks, triggered alarms with a very low error rate. The only problem was that module was too big to be mounted anywhere in the truck cab. There are usually two groups of requirements, functional and non-functional. The functional requirements are mostly about what your subsystem should do, and the non-functional, how it should do this. Applied to machine learning, the functional requirements usually include what problem the model should solve, what metrics should be used to measure the success of the model, what input the model should process, and what output is expected. Here I have some examples. Non-functional requirements are not about the problem itself, but defines the context in which the problem is to be solved. Here, I have compiled some example of non-functional requirement. Number of requests at peak time, how fast the requests have to be proceeded in most cases, if downtimes are allowed, if model will be updated, which protocols the client should use for authentication. Also some requirements considering cost of the hardware or cost of the whole solution. And maybe there are also some deadlines you have to fulfill to be able to present your model at right time. So requirements engineering is a discipline established in the software development process since long time. With its help, you can systematically help requirements for building systems of any size, any complexity, including very large ones. There are also huge books because requirements engineering on large scale encompasses many disciplines like scoping the problem, interviewing stakeholders, documenting the requirements in special way, using special templates, the life cycle management, the tooling, and many other. But if you do not have that for the much smaller part than building a complex software system, for just integrating of machine learning model into an existing system, you can master it because the approach looks much linear. It basically has a few steps. Use checklists. I will present some. Going through the checklist, ignore most of the items as irrelevant for your context. Identify stakeholders and questions which are important to ask. Ask the questions. If nobody can answer the question now, accept it. Discuss if requirement is put in right way, and document it. This is something you can do as data science practitioner as part-time job. So let's start with checklists. I recommend you to take a look at 3 of them. The first is a requirement specification template called Voler, created for any kind of software, not necessarily ML related. The template has many sections, one for each requirement category. Each section looks like this. You have a formal definition, you have example, and if you have fit criteria, if your requirements are properly documented. As you go through the template, you get a requirement mind map, which looks like this. And for every leaf, there is a section with details. Voler template. I put also a link in the show notes for this. The second checklist is a machine learning specific one that I created as a GitHub repository. You will see here a catalog of questions that are specific to machine learning projects regarding model and metrics and dataset and interpretation and so on. Feel free to contribute to this Git repository if you think I have forgotten something. Catalog of requirements for AI products. I will link it in show notes as well. The third checklist I suggest is the list of potential stakeholders. Here I have taken a stakeholder map created by the German company Sophist in a rather funny way, but still it is very meaningful. Remember, some people who might be involved in your solution may not even be known to you. For example, the people who built the microcontroller which runs your models. But if they have a specific requirement, like we can only use 4 gigabytes of memory, it would be very beneficial to know about it. So use this template to find people you should listen to. Once you have all this checklist, you will see that there are a lot of questions to ask, even if many of the items listed do not fit your context. Even if you and your product owner do the best job possible, some of the questions will remain unanswered, at least at the beginning of the project. Or the answer will be very vague. Sometimes people do not know. Sometimes people do not want to make decisions, and sometimes there is just not a person named to make particular decision. A part of it, new requirements come and existing requirements change. So it's normal to think of the list of requirements as incomplete. In the next part, I have some recipes how to deal with it. Another important point, do not just accept all the given requirements. I see at least two scenarios that are common. First, people tell you the solution instead of explaining the problem. Example, you need to use OAuth 2 protocol for authentication. The actual requirement here might be the service should be protected from unauthorized use, which you should accept clearly. But since there are multiple protocols, you can suggest another one that may also fit and is easier to implement. So once somebody tells you a solution, ask which problem they are trying to solve, and maybe discuss another options. The second case, people sometimes tell you their optional requests without knowing how much effort it will take. Example, if the customer's address changes, we want to send a quote for core home insurance right away. If you used to batch process quotes until now, this right away requires you to switch to stream processing, which requires a different infrastructure, requires a different data architecture, and generally costs a lot of work. So do not accept it, but make the client aware of implications. And maybe it's okay to send a quote until the next day, if such implications can be avoided. So do not just accept requirements, discuss them. And at last, two final factors you should also consider as constraints. First, you are building the solution with your team. So assess how much skills your colleagues have in relevant areas and how much capacity they have. Involve teams manager before planning the work of you and of your colleagues. And second, your success will most likely depend heavily on the contribution of other teams and sometimes other companies. Therefore, there are factors that can slow you down or stop your project altogether. Bureaucracy, strategic decisions at the enterprise level, such as we use cloud provider X. If that, you most likely cannot use cloud provider Y, even if it solves your problem better than X. Committees, you need approval from. The usual suspects are IT security and compliance. They can place restrictions that make any progress impossible. If you rely on other teams like platform, they may be overloaded with work or have other priorities so that you have no chance to getting their input soon, or maybe they lack the skills you need. And last but not least, politics. Sometimes there are reasons why other teams and departments are desperate to contribute to your solutions, and sometimes there are entirely different reasons. All in all, it is not technology, but organization and politics that set limits on what you can achieve. What you can do about this? While planning, get colleagues on board who have been in your company longer and can access these factors. while implementing your solutions. Get somebody on board at the management level who can solve such problems. That's it for requirements. Once you have a list of known requirements, review each architectural decision against it. Making technical decisions is what we will focus in the next episode. Thank you for the interest in the topic.